All right, guys, welcome back to part two. Now, before we move into the population example of this, which is what we're going to be doing here, I want to look at using the derivative and rates of change to make an estimate for the original function. It's kind of cool how we can do it, and it's kind of works based off of basically using kind of a linear approximation idea. So I'm going to give you kind of a visual before we dive into it. Imagine, if you will, say this is a function, right? And we know, say like right here, that's a little too linear. Let me choose a different spot. Let's say like right here. We know that the instantaneous rate of change is this, right? Whatever this nice curvy line is, it's terrible. I don't like that. I'm going to use my little fake ruler and give myself a little bit better one so I can just make it look a little better for. So this is a terrible one, but good enough. So what we can basically do is use the slope of this to make a guess, as long as we're fairly close to what our value is. So if this is our A value, as long as we're fairly close, right? So basically, for small enough h, we can use this rate of change, this instantaneous rate of change, the derivative, to make an estimate. So what it basically comes down to is it comes down to a manipulation of the formula that f prime of a is, we'll say, about f of a plus h minus f of a all over h. We'll say 4 small enough h. Now, the reason I don't give any like parameters for how small h is, right? Because what's small enough, right? Basically, for the purpose of this class, if I give you a problem and I'm asking you to make an estimation, h is small enough. If you're not sure if it's something else, like just think in the relative context to the problem, right? Let's say we're talking about a ball bouncing and we're talking about our time being in seconds. Well, then we've got to talk about like microseconds being small enough h, or maybe milliseconds, right? We definitely don't want to talk about whole seconds or minutes. It's way too much. And if we're talking about, let's say, population of a town in Europe, right? Europe's been around for quite a while, so we could use h's that are even like 15, 20, even like, pretty good size h's that seem pretty big, right? And are big measures of time, maybe relative to our experience, but relative to the existence of that space, that region, is actually relatively small. So it really is just contextual, depends on the problem. If I'm asking you to make any estimates, and I'm giving you some h value, some kind of changing value, like say 5 years later or 5 seconds later or whatever, assume that h is small enough, and that's perfectly fine. But so what we can do is we can essentially solve for this f of a plus h. So using this, we get, so using this, we get that f of a plus h is approximately h times f prime of a plus f of a. Now, if you think of this is almost like a linear function, if you will. I'm just going to highlight here. So like this would be like our slope, right? So this would be kind of like the slope, right? And our f of a is kind of like our intercept, and we're just shifting by h units, right? So I'm just going to get rid of all that. So what I want to do is I want to look at a quick little example. If f of 3 equals 2, and f prime of 3 equals 7, estimate f of 3.2. So what we have here is we know the derivative, right? We know f prime of 3. We know the original value, f of 3, and we have our h, right? So remember, so in this case here, this problem, a equals 3. So a plus h is 3.2, and h is 0.2. Very simple. So that means that f of 3.2 is approximately 0.2 times 7 plus 2. And so once we have this, we can just grab our calculators and say, okay, well, 0.2 times 7 gives me 1.4 plus 2, and we get 3.4. So what we can say is that f 3.2 is approximately 3.4. And that matches with what we are kind of using as our rate of change. So that's the way we can use this in kind of a very raw sense. But now how can I use this in terms of population? Okay, so let's do another example. If a town's population is believed to triple every 10 years, and its current population is, let's go with a nice easy, 10,000. What will the town's population be in 2 years? So we don't have a function for this, right? If we had a function model, it would be good. And you could say, okay, well, if we know it triples every 10 years and its current population is 10,000, we could create an exponential function model it. And while you're not wrong, we don't necessarily know that this population is going to continue to grow at this rate. We just believe that it currently triples, let's say that. So, too many P's in there. Believe to, well, I'll edit this as I can. Currently, triple. So I want to say currently just to add in that little idea of we only know what it's immediately doing. So this is kind of like the idea of its instantaneous rate of change, right? So what we need to do is kind of set some things up. So we could let p of 0 equal 10 be the population in thousands. There's no reason to, have p of 0 equal 10,000, right? Just say that. So then if p of 0 equals 10, we know then that, so, come on. So then we also know that p of 10 is going to equal 30, since it's tripling every 10 years. Okay, So we can use this to estimate p prime of 0. So basically what we're doing is we're using this to give an estimate for the derivative at 0. P prime of 0 is approximately equal to p of 10 minus p of 0, definitely not a triangle, 10 minus 0, which gives me 30, minus 10 over 10. So 30 minus 10 gives me 20. 10, which is 2. So we now know p of 0, p prime of 0. So p of 2 can be found like this. So we are looking for p of 2. Okay, this is obviously an approximation. Now we have to think of this as like a plus h, right? So our a would be 0 and our h is 2. So that is 2. Come on. 2 times p prime of 0 plus p of 0. P prime of 0 is 2, as we estimated. And p of 0 is 10. We are more mature mathematicians than that. I'm going to go ahead and just jump the gun and say that's 14. So, in 2 years, population will be about 14,000. So that's kind of how we utilize these ideas. It really comes back to this kind of relationship here, being able to kind of think through that and figure that out. So if you can understand that and feel comfortable with that, that's kind of all we're doing with this kind of idea of using derivatives to make estimates of what could happen in the future. So that's it for this section, guys. See you in the next section.